Okay. Can everybody see the presentation? I guess so, because I don't see any errors here. Okay. So let's get going then. So what I want to do today is, well, first I want to make some general remarks about light absorption and about absorption properties. Then I have an assignment for you regarding bilirubin, which is one of the absorbing compounds in tissue. Then I'll talk a little bit further about the absorption, not by molecules, but by particles and suspensions of particles. And then I have another assignment related to the absorption properties of blood. And after that, we'll wrap up and call it a day. So my apologies. Some of the slides, of course, I've borrowed from last year. So sometimes it just says biomedical optics. Sometimes it will just say light tissue interaction. But for the at least for today, and for please assume that this is, of course, valid for both classes. So what does our work comprise of? Well, it is, of course, a lot of physics. It is the physics of light interacting with tissue that determines what kind of measurements we can perform. There is also a very big engineering component, because we have to make these instruments. You can buy lasers, you can buy optical fibers, you can buy detectors, but you have to put them together in order to get devices that actually measure something. Of course, there's a very big biology component, because one of our main goals is to monitor disease in vivo, monitor or detect or identify. So that means that we have to understand what the biology of tissue is, how the biology influences the composition of tissue, the structural changes in tissue, and how that translates then via the physics into a measurable signal. So that is very important too. And of course, there is a medical component, because we want to apply these techniques in clinical care. We are not just developing this for the lab; we want to actually use it in hospital. So our group is located in the AMC inside the hospital. We have a lot of physicists and biologists and engineers working there. But the really strong point of our work is that we're really in the middle of the hospital, so we can talk to the doctors and ask them what they need. We can talk to the doctors to discuss how we can apply these techniques in the clinic as best as possible. So that is a very important aspect as well. But we'll start here. We'll start with the physics now, and basically look at the fundamental interactions of light with tissue, and these are absorption and scattering. Light absorption, and light scattering. So what you can see in this picture on the bottom left is just a cup of glass with water in it. There is a laser. You're looking from the top. There is a laser shining on that glass, and some of the light is passing through, and that is projected onto a screen. A cartoonish version of that is depicted on the right-hand side. So it is simply a cuvette filled with water. A laser beam is, of course, a very narrowly pointed light source. So what you will see on the other side should, in theory, just be a point when it passes through a glass of water. You can see on the photograph that it is not exactly the same. Can you think of reasons why it is not so perfect as expected?
Well, you have, of course, the interaction with particles, so you can have scattering.
Yeah, so there could be it could be that the water is not very pure. Of course, there are molecules in the water. They scatter as well, so there is some interaction with that. Yes. The glass could also be less than perfect, so there could be some I don't know, air inclusions or something in the glass itself, so that the laser beam could not be perfect. Maybe it is not this very infinitely small point, but for example, a little bit diverging. So all these factors could enter into it. Yeah. So when we talk about scattering absorption, what we'll try to do is treat them a little bit separately. But as you can already see in the simplest experiment that you can dream up with, you already have both going on. So the true separation is really hard. Okay, so let's look further to that cuvette again, looking from the top. What I did now in the glass is add a tiny bit of material so that there is a little bit of scattering, and the result of that is that this laser beam now actually does diverge in the cuvette. So you can see, if you look from the top, you can see that that light is scattered a little bit in the cuvette, and it is scattered towards your eye. That's the reason you see it. And now, if we go from left to right, there is not only this scattering material, but there is an increased amount of absorber in that cuvette. You ask, would using demi water minimize scattering? I don't think so, because if you would, normal water is already quite pure. So so scattering really, as we'll see, is really a function of particle size. So in demi water and in water, you would have molecules. These would be the same molecules. So there would not be that much change. If you would have, I don't know, if you would take rainwater from outside, which can be a little bit polluted, then it would be make a difference. But I don't think that the difference between demi water and normal water would be that much the same. Stress in the glass also affects scattering. That will definitely affect scattering, because of the if you have some stress in the glass, you get so normally a piece of glass would be just a chunk of material with a homogeneous refractive index. If light passes through such a medium, not much happens unless you make a lens out of it, and then you can refract light. But if there is stress in the glass, or if there are impurities in the glass, then the refractive index will not be an homogeneous distribution, and you can get all kinds of scattering effects. Yes, definitely. So that is certainly going on here as well. Coming back to these slides, to these photographs, you can see that if I add more absorber to the water, then the spread of the light seems to be more confined. Less light is coming towards your eye, and the whole sample by itself appears rather blackish. So very loosely defined, absorption is simply a loss of optical energy. Then a very relevant question, of course, that we can ask is, okay, what then happens to that absorbed energy? And we'll see that in a moment. I can do the same thing with for light scattering. So now I'm not adding ink, but now I'm adding small particles to this water. For example, milk. Milk is an emulsion of fatty particles from different sizes. So what you can do is just take a glass of water and add a few drops of milk, and you will see that it becomes a little bit opaque. If you add more milk, then it becomes foggier and foggier, unless you have until you have a whole glass of milk, and then you can't see through it anymore. So if you look closely to the profile of the laser beam, and I've tried to accentuate that a little bit with the dotted lines, you see that you get more or less light that reaches the detector, your eye in this case. But you can also see that the shape of the laser beam, or the shape of the pattern of the beam inside the sample changes a little bit, and that is really the characteristic of scattering. There is it is the change of direction of optical energy. There is some interaction between the light and the particles that are in the medium, which causes the light to change direction. So these are the two. Now you have two very loose definitions of absorption and scattering. So let's go on with that. So why is absorption so important? Well, if you look at the electromagnetic spectrum, this is a depiction where on the left hand you have X-rays, gamma rays. On the right hand side you have MRI kind of wavelengths, and in the middle you have techniques that work in the visible. Traditionally, all these wavelength regions in the electromagnetic spectrum have names. So they have bands called bands. So we have in the ultraviolet the A, B, and C bands, the visible band, the near infrared, the mid infrared, and the far infrared. Also in the table are then the wavelengths that are associated with that in nanometers, or in micrometers. So let's say on the left hand you have CT, and on the right hand side you have MR. In the middle you have some kind of visible optical imaging. What characteristic? So why are these placed? Can you imagine why these techniques are placed on these specific locations in the spectrum? Wavelength, yes, of course, but I could have. Yes, that wavelength is correct, of course, but but let's say that CT and SPECT are really on the left-hand side of the spectrum. MRI is really on the right-hand side of the spectrum, and optical is visible is smack in the middle. Yeah, the absorption properties of the tissue types. Somebody says bigger wavelength is deeper absorption depth. That is an interesting statement, and I will come back to that in a moment. What kind of absorbers can you think of? So let's focus on the absorption properties of tissue. Resolution, yeah. Density influences absorption. That's true. But can you think of an absorber? What could be the most important absorber in tissue? Water, yeah, it's water. This is us. We are 70% water. So basically, you can take a very big shortcut in the whole biomedical optics field. If you understand the interaction of light with water, then you're already 70% done. We more or less consist 70% of water. So whenever there is high water absorption, you can send in a lot of energy. If the absorption is high, you will not get any energy back. So you cannot do any diagnostics. You cannot do any images. But if you have regions in the wavelength spectrum or in the frequency spectrum, such as in this graph, where there is low absorption, then you can send in the energy, and you will get enough energy back to build up an image, for example. So on the previous slide, I had the spectrum on a wavelength axis. So that was from low wavelength to high wavelength, left to right. This is on the frequency axis. So that runs exactly the other way around. So in this case, MRI is on the left-hand side, and the X-rays are on the right-hand side, and the visible light is still in the middle, of course. Yeah, there you go. Also on this axis is the absorption coefficient, which is our measure for determining how strong a compound absorbs. It has units per length, inverse length, which basically means that we are measuring how much energy is absorbed as the light propagates a given length through the material, through the tissue. Frequency over there, of course, is inversely proportional to wavelength. The proportionality constant is the speed of light, c. So you can work that out. And to be complete, sometimes we don't use the linear frequency c over lambda, but we use the circular frequency with symbol omega, which is then just a factor of 2 pi. There again. And also that allows us to implicitly define yet another quantity that is related to wavelength. 2 pi over lambda is the wave number, k. The wave number, k. And I see I made a typo in this slide, so I'll correct that later and then make it up. So if we now look at these techniques that are used currently in the clinic, we can strikingly make a graph that looks somewhere like this. So here on the horizontal axis you have the depth at which the technique can look. So note the logarithmic scale. And on the vertical axis, the depth resolution. So how accurately can we measure something in the tissue? And as you can see, there is a quite striking trade-off between how deep you can look and how accurate you can look. So on the left-hand side, you have microscopy, confocal microscopy, which can only look through very thin slices, but can do that at very high resolution, of course. And then on the other extreme, there is PET and SPECT, which can image very deep. You can visualize whole organs, but the resolution is not that high. So that is also good to keep in mind. Water, of course, is not the only absorber that is present in tissue. This is a graph that adds a few more. Again, on the vertical axis is the absorption coefficient, in this case in units of inverse centimeters. On the horizontal axis is wavelength. You again see water, but also hemoglobin and oxygenated hemoglobin. Hemoglobin is the protein that carries oxygen in your body. And the nice thing you can see here is that apparently when hemoglobin binds to oxygen, there are some morphological changes in the molecule, which causes its absorption spectrum to change. So these two hemoglobin compounds have different absorption spectra, and that is of course great, because that means we can use light at such a wavelength where they are different to differentiate between these two compounds, and we can non-invasively try to measure how much oxygen is bound to hemoglobin. You have all seen, I guess, these pulse oximeters that slide around your finger. That is just a measurement that takes advantage of this principle. Other important absorbers are bilirubin, which is a breakdown product of hemoglobin, fat, melanin, but also proteins and many other ones. All right. So what then happens to this absorbed energy?
Sorry to interrupt, but how would you? There was an image on the previous slide, and I'm not exactly sure how to read it. So it's a spectra of water and some more things.
Yeah. So I'm sorry. Maybe it was a little bit too fast. So water is the black line is the absorption spectrum of water. So you can see that as the wavelength increases, the absorption coefficient increases, which means that it's more strongly absorbing. It has a few peaks and valleys, but on average, it increases. It is about minimum around 500 nanometers, which is why with visible light you can clearly penetrate through water. Then the other ones, the blue and the red one, are the red one is oxygenated hemoglobin. So that is hemoglobin which has oxygen molecules bound to it, and the blue one is hemoglobin without any oxygen bound to it. So these two have quite the distinct spectra. The funny thing, of course, is that they absorb very strongly in the green and the blue regions, which explains why blood appears reddish. The blue and the green wavelengths are all absorbed. The red light is also absorbed, but slightly less, so that can make it back to your eye. So that is why blood then looks a little bit reddish. The green one is a melanosome. These are the pigments that in your skin that basically determine what your skin color looks like. So if you have more melanosomes, your skin appears a little bit darker. Is that clear now? Do we need more?
Yeah, for me it is. What I do think is interesting is that absorption of water increases with wavelength, but in the slide prior to this, you show that there was the question that higher wavelengths have higher image depth, but water does absorb more at higher wavelengths, which kind of contradicts it, I think.
Yeah, a little bit. I would have to calculate the exact wavelengths for the MRI. But it's always a matter of proportion, right? So if you can send in enough radiation, you will still get something back, and then you can still make up an image. So it is not It is not completely absolute, and also what you can see is if you have some peaks and valleys, and this is a logarithmic scale. So if you would want to do say a measurement on the right hand side of this figure, then you would pick, for example, 1700 nanometer and not 2000 nanometer, because there's a very big factor in the absorption between that. On the other hand, of course, we all know that water absorption is high there, because that is also how your microwave functions. That is just absorption of that radiation by water that then heats up your.
I also have a question. I hope is not really stupid. But why do our veins look blue while the deoxygenated blood is red?
That's an excellent question. Does anyone have an idea? How come your veins appear bluish? Yeah, to do the scattering, that is correct. Can you elaborate a little bit more? Okay, I'm gonna. I have a couple of slides on this, so if it's okay with you, I'm going to leave the question at this moment for where it is, and I'm gonna see if I can find these slides really quickly so that I can actually illustrate the answer a little bit better. Yeah, you're absolutely right. The color of the veins does change with the depth of the vessel, so it really does matter if the vessel is superficial or if it's very deep. So it's basically the short answer is that so this is absorption as a function of wavelength. Scattering as a function of scattering also has a wavelength dependent profile, and in this case it means that the longer the wavelength, the less scattering. So that means blue light scatters more strongly than green light, scatters more strongly than red light. So what it means is that if you have a vessel at a certain depth, you shine in white light, because of this strong scattering, blue light may not even reach that vessel. So the red light, because it is not so strongly scattered, can actually reach the vessel and interact with the blood. But the blue light will just be redirected, but will never reach the vessel, and it will never interact. So that means that what you perceive is of course the balance between all these wavelengths that get back to your eye. But if you will perceive something as reddish when the blues have disappeared. But in this case, because of the strong scattering, the blue light may have never reached the vessel at all. So it just gets back to your eye, and then the region around the vessel on your skin appears bluish. The red light, which is less strongly scattered, can reach the vessels and is absorbed. So the balance between the normal balance between the red and the blues is a little bit disturbed in that case, and that's when it starts to appear a little bit bluish. If the vessel is even deeper, then it starts to look grayish, and then at a certain point you don't even see it anymore. I'll see if I can find the slides for that. That's a fun subject. Is it okay to go on, or are there any further questions? It's a good. Okay, then I'll quickly go on. So the question now is then, if that light is absorbed, what happens to it? And one way of looking at the different processes is by means of this Jablonski diagram. Are you familiar with the Jablonski diagram? See if you're not. That's okay. You are. Okay, good. So basically, it is kind of an more or less. Okay, that's good. So what it basically shows you is kind of a depiction of the energy states of a molecule and the possible transitions that can occur between these energy states. So you have the thick lines in here are the vibrational ground states, S0, S1, S2, and then the thin lines that are slightly above that are higher vibrational states of these ground states. And then not in this cartoon, but we can have that too, are dashed lines, so-called virtual energy levels that do not correspond to a specific configuration of the molecule. The bigger diagram in this slide has only S0, S1, and S2. You can also have on the horizontal axis some additional lines for spin multiplicity. So that means that the singlet states are on the left-hand side, and the triplet states are right next to that. But the idea remains the same. If you go, so the multiplicity increases when you go on the horizontal axis between singlet and triplet, and the energy increases if you go from S0 to S1 to S2, etc. So these are properties of the molecule. And then the arrows in the diagram indicate what happens when we shine light. So in this case, the green arrow is an excitation. That's a photon with energy E is equal to h times v, or h times the speed of light over the wavelength. When you have an excitation photon incident on that molecule, so you can then excite the molecule from its ground state to a excited state, and once you have that, from that a few things can happen. You can have, for example, non-radiative relaxation to the ground state, which means that there is some relaxation of the molecule to the ground state. Non-radiative means that there is not a new photon emitted. It is just the energy that the photon brought is transferred, is just converted into heat. And that heat is then transferred to the surroundings by the molecule. Still with me? Okay. So if you that's one of the most basic processes that can happen, and of course we can try to use that or try to exploit that. This equation is not here specifically so that you need to learn it by heart, but just to give you an idea what's going on. This is the regional heating of tissue. So we have a T temperature at a certain coordinate R in the tissue at a certain time T, and with this equation we can calculate how the temperature in space and in time changes when we illuminate it with tissue. So you see a couple of constants in there. There is the density of the tissues. More tissue means more absorption. There is specific heat of the tissue that will be tissue dependent. So certain tissue that will depend on the tissue type. There's temperature, of course. There's conductivity of the temperature, and then in blue there is the optical, basically the process, the parameters that describe the optical processes. We have this absorption coefficient again per unit length per meter that describes how strongly the tissue will absorb light, and we have a fluence rate here, phi, which has units watt per square meter. So what it basically tells you is how much energy, joules per second is watts, you deliver to an area of tissue, and that area can be defined outside the tissue. You can also define that inside the tissue, so then it will be the energy that flows through that area per unit second. But this basically tells you how strong your light source is, and the product of these two, as you can see, becomes watt per cubic meter. So basically, The product of the absorption coefficient and the fluence rate tells you how much energy, how many joules per second per unit volume you absorb. So how many energy you actually dump into the tissue. So what you would typically now R is just, in this case it is just the question is what is R? In this case it is just a spatial coordinate inside the tissue. Of course, if you would want to solve this equation, you would need to define some coordinate system, but in this case it is just taken generally. Well, this is typically the kind of the kind of equations that you need to solve if you want to calculate the distribution of temperature within the tissue. And just to give you an idea, feeling about what temperatures we're talking about, if you locally heat the tissue up to temperature that are higher than 41 degrees, you can already have denaturation of proteins. So you can already do damage there. If you crank up the laser a little bit higher and increase the temperature to over 60 degrees, you can already start coagulating tissue, burning tissue. So you can, there's a couple of uses for that. You can use that, for example, to weld tissue together, like stitching, and then using a laser, you can basically burn it together. But you could also direct it to pieces, parts of the tissue which you suspect of being a tumor, for example. So you can treat it that way as well. This is a nice technique that makes use of this absorption. It's called photoacoustic imaging or photoacoustic tomography, and the idea is that you use a pulsed laser to shoot light very locally at a piece of tissue. That light will be absorbed mainly by the blood in tissue, but because the laser is pulsed, and if you think back of the previous equation, which had a component of time in there, if it is absorbed very quickly, it will generate an ultrasonic pulse, just a little bit of expansion due to the absorption. And that ultrasonic pulse can then be detected using, let's say, a normal ultrasonic detector, which you've also seen in just a normal echography. So you can pick up that pulse, and then if you do that at a few different locations, then you can calculate back where the absorption took place, and you can make a reconstruction of the basically of all the absorbing compounds inside the tissue. So what you see there on the right hand side is a reconstruction, a photoacoustic reconstruction of the blood vessels around the tumor in a mouse. So you can then reconstruct this vasculature. People want to know that because if you want to now treat this tumor, then it's very convenient if you know how many vessels there are, how they are aligned. If you want to get medicine to the tumor, you would need to inject it, so you need to know how many vessels there are. If you want to do damage, you also need to know it. So that is a very nice application of this. Okay, then the second mechanism is called fluorescence. So again, we have the Jablonski diagram here, and again, the green arrow signifies an excitation photon. So the photon excites the molecule to, in this case, in the drawing, to S2, to an excited vibrational state of S2. And from that, there is first some non-radiative relaxation to the lower excited state, and then additional non-radiative relaxation to the lowest excited state, so to the S1 state. That energy is again lost to temperature. But what happens now is that, in contrary to the previous example, is that from that S1 state there is now a decay to the ground state by emitting a photon. So that is So now the energy is not converted into heat, but it is converted into another photon, which is then emitted. So you get new light. So as you remember, on the vertical axis of the Jablonski diagram was energy. So that means that the longer the arrow in such a diagram, the higher the energy is. So what you can see is that in this case, the excitation photon has a higher energy than the emitted photon. So the fluorescent photon, the energy of the fluorescent photon is less than the energy of the excitation photon, and because of this inverse relationship between wavelength and energy, that means that the fluorescent photon will have a longer wavelength than the excitation photon. So basically, you shine in, let's say, blue light, and you get back red light. This process takes relatively little time. So from excitation to emission of the photon, that can be in the order of picoseconds, but can be up to microseconds. So it can take it's fast, but not but measurable. Microseconds is easy measurable. Well, of course, you've seen, I don't think I have to elaborate a lot on that. You have seen fluorescence imaging, fluorescence microscopy before, I guess. So on the left-hand side is fluorescence microscopy, where you actually use this this effect in a microscope to probe different compounds. As you can imagine, every molecule or every constituent in tissue has its own unique Jablonski diagram. So if you excite with let's say green light or blue light, then depending on that on the tissue type, depending on that specific diagram, you will get a photon of a specific wavelength back, and you can measure that. You can encode that into these beautiful images. That's for microscopy. There on the top, you can see a clinical example. You can also use this in the operating room, for example. You can inject a fluorescent compound in tissue. These tend to accumulate around tumors. So if you then wait a little bit and then switch on the blue light and then watch for the fluorescent photons, you can find locations where this fluorophore has accumulated, and then hopefully that correlates to the location of the tumor. Does anybody know why this happens actually? Why would it accumulate in a tumor? Yeah, leaky blood vessels. Yeah, so the tumor is a very impatient piece of tissue. It wants to grow. So it does not take very much time and very good care of building the vasculature. It just wants to grow. So the vessels that are around tumors are usually a little bit sloppy and a little bit leaky. So that means that if you inject some medicine or some compound like a fluorophore and have it circulate in your body, in normal blood vessels, it would stay in the vessels and nothing would happen. But around the tumor, it leaks out a little bit, and then it turns up in the tissue. Increased blood flow to the tumor can also happen. Of course, that is more something that is associated with the larger tumors. With the smaller tumors, that is not so much happening yet, but that is also a factor.
I'm sorry, I have a question.
Yeah.
It may be a little bit not on the light tissue interaction, but about the cancer and with the leaky vessels you mentioned. Isn't it also problematic that there's just a lot of blood leaking from your veins, or not a lot, but it's more like you have some leftover blood around in your body? Is that not also problematic?
I'm not sure if I completely understand the question. Can you?
Yeah, no. I was thinking if your blood vessel is leaking, then blood is just around in your body, and I think that's also problematic, because maybe maybe the blood will get old, and I do not think that's very good for your body either, right?
No, yeah, that can be, but on the other hand, your body has a pretty has a pretty good mechanism of dealing with that, and you have experienced that, because I'm sure you've had a bruise at some point, and basically what a bruise is just damaging blood vessels so that blood leaks into the tissue, and after a couple of days, it goes through a beautiful spectrum of colors usually, which tells you that there is some kind of enzymatic reaction going on that converts the hemoglobin to bilirubin, and then etc.
Yeah, so, no, totally true. Yeah.
Remark on fluorescence. You can do that with only one excitation photon, but you could also do that with two photons. If you have two photons that together have exactly the energy to bridge the gap between two of the levels in the Jablonski diagram, then you can use these two photons to make that excitation. And after that, the process is the same. Once it's excited, you have a little part of non-radiative relaxation, and then the final step back to the ground state is under emission of a photon. The interesting thing, of course, now is that if you look at these two excitation photons individually, the idea is to have them interact with molecules at exactly the same time, so that they both transfer their energy, so that you can make this jump. But looking at the diagram, this now means that in this case the energy of the fluorescent photon is higher than the individual energy of the excitation photons, and then vice versa. Looking at the wavelength, that means that the fluorescent wavelength is now a shorter wavelength than the excitation photon, and that can in some cases be very, very beneficial. For example, if you want to look at and then again I have to skip a little bit ahead towards scattering, but now if you want to minimize scattering, you would like to have a longer wavelength, because they scatter less. So with this trick, you can use longer wavelength photons to excite fluorescence in an image, so you can look a little bit deeper, for example. Again, this takes place at picosecond to microsecond timescales, and the drawback is that you need a very large number of photons, because it only works if you have two photons that arrive exactly at the same time at this molecule and exactly transfer their energy at the same time, so to get this excitation. If you have if you're with outside this picosecond to microsecond range for this whole process, if the photons arrive at longer times, then it will not happen. Is multiphoton always to S1? I don't think so. I think this is just how I drew the cartoon the last time. I would have to check, but I don't think so. All right, this one is also intriguing. This is phosphorescence. Again, a Jablonski diagram, but now I've added the triplet states as well. So again, the thick lines are the ground states, the vibrational ground states, and the thin lines are the vibrational states. And now next to the singlet states, next to the singlet states, we also have triplet states. So what happens here is that again, we start with a photon that excites to a higher state. There is some non-radiative relaxation to the vibrational ground state, and then instead of decaying further within the singlet state, we now have some energy coupling, so-called intersystem crossing, to lower triplet state. So So the energy of the molecule is basically transferred without radiation, so without emitting a photon to another to another toestand, to another of the molecule. And so from that state, yeah, thanks. So from that, it can then again decay to the S0 state, and then it emits a photon again. Well, and again, now looking at this diagram, you see that the excitation photon has the highest energy, that the phosphorescent photon in this case has lower energy, which means in terms of wavelength that the phosphorescent photon has a longer wavelength than the excitation photon, just as was the case with normal fluorescence. But the peculiar thing about this is that the process takes much longer. So if a molecule gets caught up in this triplet state, it can stay there for much longer. So it will be in this T1 state for milliseconds to possibly even hours before it finally emits that phosphorescent photon. So that is something that you can utilize. For example, this is one utilization of that phosphorescence. Here on the left-hand side is again the Jablonski diagram. This time without the fancy colors, but the principle is the same. You have excitation from going from left to right. You have excitation from S0 to S2 in this case. You have some decay. Then there is this intersystem crossing, this energy transfer between the singlet and the triplet and the ground triplet state. And once we're there at the T1, then as drawn here, three things can happen. So the first is it stays for a while in this triplet state and then emits a phosphorescent photon and then decays to the S0 state. That is what we discussed in the is that yellow? Yeah, that is the same. Yeah, exactly. If the photon is if the molecule is still in the T1 state, of course you can send in another photon, and maybe that gets absorbed. So you could also have triplet absorption from where it can fall back again to the triplet state. So you can do some probing with light on that on these states as well. But what can also happen, and that is interesting for diagnostics, is that if this molecule, this metalloporphyrin in this case, if that is in close proximity to oxygen, then it can transfer energy to oxygen. Oxygen is a little bit peculiar because its actual electronic ground state is T0, so it is normally in a triplet state. But when you excite it, you can excite it to the first singlet state. So that is on the right-hand side of that graph. So if that energy is transferred to oxygen, so from the metalloporphyrin, if it is transferred to the oxygen molecule, then it is gone. Then it can no longer be. Then it is no longer possible to emit a phosphorescent photon. So that means that if you have this kind of molecule, and you would normally, I'll get to your question in a moment. If you would normally see phosphorescence, now in the presence of oxygen, you will not, you won't see that anymore because the energy has transferred to the oxygen. So you can do a type of measurement, as in the graph there, where you have a very short pulse to excite the metalloporphyrin molecule, and then since this process is pretty long, you can just take a time in measurement a time to monitor how much phosphorescence you will see. If there is no oxygen, or if there is not a lot of oxygen around, then there will be kind of continuous long enduring phosphorescent emission. That is the dotted line in the graph. Low oxygen tension, low PO2. But if there's a lot of oxygen, of a high oxygen pressure, then this fluorescence will be quenched, and you will not see a lot of fluorescence. Your question is, could this also lead to photo bleaching, or is the T1 state more stable? The T1 state is more stable. Is even more stable. So I don't think so then. Okay, and I know it's almost time for a break, so bear with me for a few more slides. This was, we already had this one. Yeah, this is an not the prettiest slide, but to show you an actual measurement that this can actually be done. This is a phosphorescence lifetime measurement done on the kidney. As you can, the sketch on the right-hand side just shows two parts of two layers of the kidney. But the point is that, and that is then the cartoon on the left-hand side, you don't need very fancy equipment in order to do this. And also, as you can see on the horizontal scale of the graph, the timing is in the order of half a second in this case, which means that you basically have a lot of time to do these kind of measurements. So it is something that can quite easily be done in the clinic. And in this case, the goal was actually to measure how much oxygen is present in kidney tissue. If there is not enough oxygen, then the tissue cannot function, of course. Final remark, and then for that I'll go back to this Jablonski diagram with the metalloporphyrin and the oxygen again. If this mechanism is used to transfer energy to oxygen, it goes from that triplet state to the S1 state, and it's called singlet oxygen. And singlet oxygen is highly reactive. So, for example, if you have singlet oxygen near DNA, it can easily damage the DNA. It can easily damage other molecules in the cells. It can do lots of damage. So you can use that for therapy. If you have a tumor cell that you want to kill, then you can use this mechanism to basically have the oxygen do it for you. This is called photodynamic therapy. The principle is then as follows: you inject a chemical like this metalloporphyrin in the body. Your bloodstream makes sure that it is circulated throughout your body, and again, these leaky vessels. Through these leaky vessels, you have the effect that it accumulates, that the metalloporphyrin actually accumulates around the tumors. So now you have a higher concentration of this metalloporphyrin around the tumor. So then, with light, if you suspect where the tumor is, if you know the location, you can you turn on the laser and you make this whole excitation cascade. So the excitation, then the intersystem crossing, then the coupling to oxygen, and then the oxygen does its damage. It's selectively destroyed there. The nice thing about this approach is that if you inject a chemical, the metalloporphyrin, and if you keep the light out, nothing really happens. It is eventually it will be cleared out. It is the combination of the metalloporphyrin and the light that makes this whole cascade. So you can do very targeted treatment this way, very localized treatment. It is not as with let's say standard chemotherapy, which ends up in your whole body. This is just very selective. Of course, you have to be a little bit careful because if you illuminate at locations where you do not want to treat, you can also do damage. So it can happen that people who get this therapy have to stay in the dark for a few days after the treatment. The light will pass if the So you can. The question is, will the light pass through the tissue to reach the substance? It depends a little bit. So you can. If you turn on the light source really hard, then some light will hit it. But you could also imagine that you take an optical fiber put it in a needle and bring it close to the tumor site to get the light there. So there are some ways of doing it. But most of it is, for example, one of the most used locations is in the nasal cavity. So because that's really hard to reach otherwise. So so then in the nasal cavity, there's you inject these things, inject this metalloporphyrin systematically, so it accumulates there, and then there is some kind of fiber-based, basically hooking up a fiber through the nose to reach the nasal cavity, where you can then do the treatment. All right. Quick. No, let's take a break here, because otherwise I'm going on for way too long. Let's say 20 minutes, and then go for and then continue. So back at 3 o'clock. Okay. I'm going to stop the recording, so I'll put it back later on, and I'm going to turn off my camera, but I'm still here. So if you have any questions, feel free to ask.